All right, Jason, please take it away.
All right. As Ben said, good afternoon or good morning, depending where you're at. Again, my name is Jason Danielson. I am the building envelope national architect, the SME and central office. And just real quick, just going back. So this is the building envelope, building enclosure, chapter 3. The bulk of the content is in chapter 3. There is some in chapter 1, and I'll be touching that in a second. So just a few things here, just real broadly. There was the flood resistance design that got moved to chapter 4. So that you'll see, and here's an example. This was P100 2022. And then right below that is, so for the P100 2024, within table 3.1, the sub-numbering has returned, and it's just easier for referencing and for navigation. If people joining can mute, that'd be great. So chapter 3 is going to reference this in quite a few areas. This is the facility definitions, and it touches on a few things: essential facilities, critical action facilities, and mission critical facilities. So those are higher risk facilities, and so some of the performance that we talk about in building enclosures or the building envelope will reference some of these facilities. And that's at 1.3.9. So I have this set up right now. It's chapter 3. It's broken up into it's really kind of 6 different kind of sections, and within that there's supporting material for each of these. And so I'll start off, and like with this first one, we'll get into table 3.1, which is at the front end of chapter 3, and then there are narratives that are further in chapter 3. But all of that will kind of be everything that's kind of related to, for instance, this first one, water penetration resistance, will kind of be covered in that section. So first one here, chapter 3.1.3, the enclosure performance table. And this one is talking about, this is the water penetration resistance for fenestration. Previously, we had a CW, CW30, AW40, some other window kind of performance criteria. Always had, on most jobs, always had difficulty as far as like people within industry or on the team, as far as not kind of different takes on that. So where I ended up going is replacing those and trying to be clear with that and having design pressure requirements. So this is showing baseline, the 6.24 design pressure. So this is, and just backing up a little bit again, this is just a refresher for those that are kind of newer to P100. A lot of times we'll have baseline plus those tiers. We don't want to overinvest in certain buildings, but we also don't want to underinvest. So there's trying to determine kind of where the building kind of fits, appropriately. So what this is showing also and you'll see this as far as like tier 2, talking about mission critical facilities, what I had just talked about earlier, or high rises or ASC 7, places that are kind of in hurricane prone locations. They may require a little higher tier than some of the others. So that's kind of what's going on with that. This also ties design pressures to, like I was saying, the ASCE 7 wind speeds, and then facility types based on risk. And I'll mention this a few times. AMA, which is really kind of set up by the fenestration industry, and they're kind of, it's a self-promoting, self-policing kind of thing. They request a 1/3 reduction. And so we're not following, so we have a no 1/3 reduction in field testing procedures. The intention there is it's the delivered product is what we're most interested in as an owner. So if they choose to go with a higher testing criteria in the factory, that's something that they have the ability to do that. So I'll keep going here. So water penetration resistance below grade, the ASTM testing methodology, those ASTM sections are referenced. Water penetration resistance, the roofing, the horizontal waterproofing, so flat surfaces that might be under like a parking deck or something like that, as well as roofing. This was just a reminder to include the conductivity scope for testing. A lot of times when you're doing ELD tests, making sure that you have that scope associated with the ELD. And it's calling out to test before placing any overburden, and that there may be overburden provisions for passive and active monitoring. So you can hook up the ELD, and passive meaning you can bring the equipment back out later, but you actually have all the kind of the grid or the conductive membrane installed and the links to set up, and you can bring that equipment out. Active monitoring, it would be hooked up to your BAS system. 3.3.1, water penetration resistance and fenestration. Here's copy, these are screen captures of where you'll find this and the differences that have happened. So on these projects, you always have there's a question of how many samplings. So as a kind of default, go with 2 test samplings per condition as a typical minimum, and include air and water testing for untested systems. And I mention again the 1/3 reduction for field tests, no 1/3 reduction. 3.2.3.2, water penetration resistance, roofing horizontal membrane. This was talking about, this has a couple of new pre-tests for roof assemblies. This is the UL 580, the ANSI FM 4474, and the TAS 114. And this is, you'll see this, this is Florida has a lot of this as far as, and they're really kind of leading that and kind of in making sure we're managing that risk. So with that, I'm going to, those are kind of the broad kind of changes to the water penetration resistance. If anyone has any questions at this point, if not, and we can also have questions at the end too. So
yeah, currently there are no questions.
Okay, great. Jump right into moisture and condensation control. So this chapter, and this, so in the way I have this kind of set up, so you'll see the enclosure performance table will always have those, the kind of the green or the blue bubble on the right, and then the narrative is kind of swapped. So just if you're wondering as far as format and where to find these things, but it also has the title up there. So 3.1.4, enclosure performance table, and the moisture and condensation control, moisture control for opaque assemblies. This shows the expanded list of QC testing standards, all of these ASTMs, and just which complete is a better kind of comprehensive testing for that assembly. Chapter 3.1.4, moisture and condensation control, condensation resistance for fenestration. This provides a little background to why those certain reference standards were referenced for each tier, and an expanded list of QC testing standards. So this is going through, we're talking the NFRC 500, we talk about the thermal analysis and the modeling, and then also these some of these additional tests, the IGCC certification and some others. The green roofing system, the updated design and media requirement, so basically this is really just consulting with central office, landscape SME, if considering a green roof. That's really kind of what this update was. And the 3.2.4.1, moisture control opaque assemblies. This is analyzing the performance of unique or custom opaque assemblies, and then to use 2D or 3D thermal or hygrothermal analysis tools, and then the ASTMs and the ASHRAE and ISO 10211 and CSA ZSO 10. So this these are really going to get into the thermal short circuits and the analysis of that. And so that's another thing with the thermal, is we really started to hit and that starts to affect the moisture control, understanding kind of where the potential thermal short circuits are, and we're starting to address that in this version. And 3.2.4.2 condensation resistance with the fenestration, similar things. And this is, this is the modified text that's in there. And again, analyzing the performance of the fenestration and talking about 2D or 3D thermal and hydrothermal example conditions. Skylights and sloped glazing, just a real simple, just providing a controlled condensate path. It was a little bit vague before, and just trying to clear that up. And that's really it for moisture and condensation control.
Any questions out there? We currently don't have any in the Q&A.
Okay. All right, jump right into air tightness. Air tightness was something that we made a pretty big jump. And part of this was in response to, there are a few things that were triggers for this. One of them was the NIBS DLR study. Bobby Wager from our group really led that exercise, and that was about a 1.5-year exercise. And that, I don't know if others have seen already kind of before presentations on that that were related more to the building enclosure program, and looking at different ECMs and which ones were provided the best kind of bang for your buck, and one of those was tightening up our enclosure. So this one, 3.1.5 enclosure performance table. This is the air tightness and air tightness for the fenestration. This defines high-risk facilities and the weather locations to meet Tier 1, kind of what I talked about before. That's kind of the mission-critical facilities and some of those other facilities, as well as kind of if depending on where you're at for weather. And then clarifying the requirements for punch windows, curtain wall, window wall, and storefront locations. Before, it was a little bit ambiguous. We were missing some of that kind of detail. We kind of hit punch windows, but there wasn't as much. There are slightly different requirements for each of the other conditions. So this starts to spell that out a little more. And then clarifying durability requirements. And then chapter 3.1.5, and this is the location for that, is the air tightness, the enclosure, for the enclosure air tightness. So this is what I was talking about before, that baseline is at that 0.17. We previously were at 0.25, which matched the Corps of Engineers. And as far back, 2018, before that was 0.40. We've started to kind of track a lot of the results of what we've been getting for blower door tests, and we've been finding that we're very easily been able to match, be able to get match this 0.17 and sometimes beat that. We've had some that are at 0.06 and then 0.06, 0.07. So it's very achievable. And we saw a lot of, based on that DLR, the NIBS DLR study, the potential paybacks are high. And then in additional, the Tier 1, talking about air infiltration matching bias, which is passive house. 3.2.5.2 air enclosure air tightness again, and this is the narrative portion of this, and this is saying to consider diagrammatically demonstrating the continuity of the air and thermal barriers on the drawings. And this is an industry best practice. Right now, we're saying it's a consider, it's not a requirement. So make sure you kind of check that. A couple of these at this point are just proposing that as far as making it a requirement. And then the improvement of building envelope performance as part of the net zero study that I talked about. And then quantitatively and qualitatively measuring existing performance for major modernization. So doing that blower door test before you do the work as well as after, and understanding exactly what your improvement was. And by doing it before, you also have a better idea of exactly how your building is currently performing, having concrete numbers and rather than kind of a swag, but to know exactly what that improvement and to be able to kind of gauge what that improvement will be. And then the last thing is including garage doors and energy models where they are integral to air and thermal barriers. This really, think about basements of a courthouse and whether or not that's an active, if it's parking in the basement and you have active parking, if it's a courthouse, and it really is kind of determined on the security of that. If security requires that door to be closed most of the time, that the garage door should be included in that energy model. That's really your line, and your thermal line as well as your vapor. That outside wall that's aligned with your garage door, then it really needs to be at the roof of that parking garage. So it's definitely something to, if you have any questions, feel free to reach out. And it's a pretty common topic to have, and just understand where how your building is being run. From that, if there are any questions.
There are none currently. Maybe just
Okay.
pause a second and see if anybody adds.
All right. I'll jump right into thermal performance. So chapter 3.1.6, this again, the table 3.1, thermal performance, and here are references that are to IECC, ASHRAE 1365 RP, the BETB guide, and the low TEDI guide. So these are all references for that, what I was mentioning before, the thermal short circuit, and it's really a push that we're starting to see. It's much more prevalent in Canada. They're leading on that, and so this is one that looking to see some of that benefit. 3.2.6 thermal performance. So a few of these takeaways. This is mitigating the effect of thermal bridges, including material conductivity and thermal continuity. And you can see some of this on the right. You're talking about thermal breaks, talking about low thermal conductivity materials, closer alignment of the insulation and thermal control layers between those adjacent assemblies, converting continuous thermal bridging components, I'm talking about Z-girts, etc., to discrete components like a clip, and then providing insulation around structural. Others topics that were covered, the building envelope thermal bridging guide, that reference was also provided again, and then analyzing, just as a general, and kind of talked about this before too, analyzing unique spandrel assemblies that are part of a curtain wall as an opaque assembly. And this, another related to the aged materials of aged thermal performance of materials, and I'm thinking specifically insulations, but it could be lots of different materials. Right now, specifically insulations, the R value is measured at 70 degrees. It's not measured at its full operating temperature, and that's where we're trying to. So there are a few things here. Accounting for the aged thermal performance of materials, some insulations start to off-gas and they start to lose their performance. So out of the box is the best that you're going to get. Some insulations also perform very poorly when they're wet, next to nothing. Some insulations also go reduce by 3/4 or more of their R value by getting to like colder temperatures near freezing. So thinking about that a little more, and that's where we're talking about kind of performance through that full range of seasonal temperatures. What is to the extremes, both the hottest as well as the coldest, and understanding kind of what those are. And I mentioned already before, for modernizations, consider measuring performance before and after work. 3.3.2 0.6.2 window frames, thermally break aluminum frames per NFRC 600 in climate zones 2 through 8. So this is where you'd find that. And then 3.374 insulation. The insulation considerations for historic properties, and then insulation options and factors, the various potential insulations for historic. They're like, for instance, vacuum insulated panels. You might have like a mid-century modern that is a historic property with no kind of parapet and looking for super low profile. Does it make sense to go with a vacuum VIP high performance insulation, which can potentially be R50 depending per inch? Is that something that makes sense in that particular instance? And from there, any questions on thermal performance?
Currently none in the Q&A.
Okay. We'll jump into building enclosure commissioning. So chapter 3.1.7, this is the building enclosure commissioning. And we talk about defining the high-risk facilities and the weather locations again to meet tier 1, and verification of the air, vapor, and thermal barrier continuity during construction. This one will come up again in the narrative, but this is something kind of what we found on a couple different projects now, best practice. We're getting in there and actually starting to do with the infrared or some other tools, being able to go to see whether or not you had that continuity between that wall and that roof condition. Madawaska is one example, was at the wall and the foundation. And if we hadn't kind of caught that before closing up both ends, the potential of having condensated or air traveling through that exterior wall could have created condensation within that wall. And then also, as far as if you're looking to get you meet that 0.17, having that tight, all of these areas that are, because that would be pretty, because for Madawaska it was around the entire building. And we in Harrisburg Courthouse used that also, which was really helped with a very difficult enclosure system, and we were able to beat the requirements on that one using the same verification during construction. 3.2.7, building enclosure commissioning. Some of these things are super basic, but just making sure that it's clear and it's not something that we're going to have any kind of bird dog on every job, because it's really kind of again, it's kind of should be best practice. So performing the enclosure before installing finished materials, this probably makes sense to a lot of people. You don't want to put your drywall up and then because you need to have visual access to if you're doing an air or water test on the interface between a window and the adjacent wall. If you need to be able to have visual access to that. So if those finishes are put in, they'll have to get removed in order to do that testing. Establishing a failure protocol early. This is, before construction has started, you understand if there's a failure, exactly what are the is it test and then pick another sample, because you're not testing every location, you're testing a sampling of the building, and that's usually a percentage or I was talking about before, as far as a minimum of two per condition, 2 per detail condition, but establishing that failure protocol early and making sure that everyone on the team is aligned and bought in on that. And enclosure commissioning valid 6 months after the substantial completion. This is one where we've had phased projects, and it starts to get extended out and protracted out so far that we may start to get to a point where it may not be valid anymore, but just because the the phasing of the project. So that's one thing, just to kind of make sure that we have our, that we're covered. And just a general mock-ups for anything that's new or atypical. And this goes back to risk and just managing that risk. 3.3.8.2 air barrier testing. There's just an IGCC reference updated. And then what I was talking about before, this was in with that construction. So and it's an ASTM 1186, and that was the infrared and the smoke pencil I was talking about as far as like during construction. If there are no questions, I don't see anything in the Q&A. I'll jump right into service life. So in table 3.1, 3.1.9, the enclosure service life, this defines, again, the high-risk facilities. This is where high-risk facilities are a tier 2, and for each of those, it's in walls, roof, and fenestration, and that's called out. Another is the manufacturer's warranty certificate, and this is for roofing, and that roofing warranty also replacement includes labor and materials. So just trying to clarify that and make sure that that's clear up front. 3.2.9 enclosure service life, and showing the examples here and where they're located. And this was really pretty significant updates. That service life must be based on proven industry best practice and must be designated against the potential for deferred maintenance. So if this is something that we don't have any testing criteria or proven systems, trying to have that the best we can as far as getting the based on best practices. And it's a little bit ambiguous, but we're just trying to be able to get the appropriate service life and making sure that the systems that we pick support that service life. 3.3.4.1 connections, fasteners, and miscellaneous metals exposed to weather. This is real quick, just a clarified material for marine environments. Before we had stainless in there, we just call out now SAE 316, get a little more specific on that stainless, as well as a couple of other options that are out there that, and this is just for marine grade. I mean, you could do that in other areas, but it's probably an overinvestment. But potentially using brass, aluminum bronze, or silicone bronze for those materials, as well as aluminum and copper in limited applications. 3.3.4.4 is a new section that's sealants. And this is one that big picture is just kind of talking about redundancy in sealant joints. And we're really starting to rely a lot on sealant joints and trying to become less reliant on that, and because it's a pretty significant wear item. But this is one too that and I have so this whole section is new. It refers to ASTM C1193. We have for those sealant joints systems that are a barrier system, which is mean we're relying 100% on that sealant. We need to have that, and we right now kind of reference PCI, Precast Institute. But what PCI didn't do, it talked about panel to panel. It was very clear about that kind of that two-stage sealant. So the inner line being your primary seal, and then that kind of weeps out to your exterior. And then that outermost line is really, for all intents and purposes, a rain screen. And so that outer is one that can, it'll deteriorate, quickly within, 10 years, 5 years, whatever that is, maybe 20 if you're lucky. But having that interior being your primary and that being protected, that can go longer. And so it's really just a matter of replacing that outer line. But what PCI didn't do is they talked about panel to panel, but they didn't talk about anything that was adjacent to that, including a window that might be in that panel. And so that's one that we had a couple of different projects that had a two-stage sealant joint, kind of sealant acting as a rain screen, then coming up right next to another that's a single line, and we're relying on that line. And if you have any kind of failure, that's going directly into the building and then damaging finishes and affecting tenants. So it's something that it was obvious, but just making sure that that's much clearer now and it's spelled out. And again, if we can reduce sealants, we really, that's the ideal is to come up with systems that are less reliant on sealants and less labor or O&M intensive. 3.3.5 masonry and concrete materials updated requirement and service life. Or sorry, and this is kind of the same. Very similar as far as talking about the two-stage sealant joints, and then there's a section here, concrete specs to be performance-based, including the allowance of several reference standards. 3.3.6 fenestration systems. This is strategies for different window replacements, and so this is talking about also a lot of these we're talking about double or triple glazed. What are different options, vacuum insulated glazing, and just kind of laying the table of what potentially is out there, and that the service life must be taken into account for the potential of deferred maintenance. Once again. There are others as far as like in this section 2, single pane windows. Potentially there is rather than doing a replacement with a new window system, potentially you could do an inner secondary window and just doing that payback analysis and understanding kind of what your options are and what that payback is. 3.3.6.1 windows. There was just a minor kind of as an updated reference to ANSI AMA 101.17, and then talking again kind of historic window strategies and what potential options you have, and kind of describe some of that just now. 3.3.6.3 entrance doors. Just it's following the service life of the windows that were described previously. And then 3.3.7.1 roofing. The couple of things that were added into this section, which are highlighted in the red, is the requirement for having a solar ready roof design. And if there's any kind of likelihood within that service life of whatever your roof is that you're going to be doing solar, that you have the infrastructure set up ahead of time, so you're not having to go in and kind of tear that roof apart, and kind of that you have the conduit that's already there, and potentially if you have any support, unless it's a ballasted system. But if it's something that's being kind of attached to the structure, that some of that is that infrastructure is already set up. And recommendation to perform hydrothermal analysis before selecting a roofing membrane system. Best practice. 3.3.7.2 re-roofing. And this talks about, and this is so right now on every roofing job, we typically throw the insulation away and put new insulation in. But there are some insulations that are more durable and something that you potentially could be reusing. So this is talking about, depending on where you are within the service life of a roof, if the roof is, if there is still some service life left of that insulation, depending on what it is, any potential to be able to reuse that. And we're talking about edge integrity, whether it's structural, whether or not structurally it can be reused, as well as any kind of its thermal performance. If there has been a reduction in thermal, understanding exactly what that is. That's all I had for that section. We've got a few here. Let's, Lance, I see you mentioned, as we move to electrification, you mentioned about taking care of efficiency items first as it relates to the enclosure. What should a building manager, project manager do to determine what they do first in their building's facade? That I think is one that just to understand, and I was talking about, examples of, you could do blower door tests, you could understand exactly uh, how, as far as air infiltration, whether or not that needs to be improved. Need to look at, a lot of these could be, studies that are done by your AE as far as whether or not there are, the window systems need to be improved in any way. Do they need to be replaced, or can they be improved, with some of the secondary windows, or even sealant going in and just being able to update, and improve on water infiltration as well as air infiltration. I think those are some right off the top as far as thinking of, some of these that would be the first thing. If you look at kind of I don't have an image in this presentation, but I've had it in others. If you look at the net zero pyramid, number one is programming, but right above that, as far as bang for your buck and what you really need to be focused, is the improving the building enclosure, because by improving your building enclosure, you can potentially reduce the size of your equipment, and all of the other is HVAC and some of these other equipment can potentially be downsized, and you can see some savings as well as embodied carbon reductions. John Corbett, with all the P100 updates, do we also get an update on the cost estimating tool to match these changes? We did, and I'll leave that open. I don't know, Lance, if you want to talk about this at all.
Yeah, I can talk about this. So yeah, as we were doing P100 this time, we worked very closely with the cost estimating group and their contractor. And so the P100 steering committee actually, we sent them the change proposals, and they gave us potential cost impacts. And so we had that as part of our decision making as we were looking at what to include into P100. And so they've been with us since August, working with this on these updates with P100. And then in the end, yes, they're ready with the updated tool to be able to put these changes in and be ready to go. So they are much further along this time than they've ever been before. And it was actually great for us because we could then take those potential cost numbers and give that to leadership as to why we were doing something or why we weren't doing something. And so I think that's going to be the way we'll move forward in the future, is continue that effort and make sure cost estimating and P100 are working hand in hand here. So
thanks a lot, Lance. Lance, you had another comment on this as far as service life, talking a little bit more roofing related to functions within the building. I covered this just a little as far as talking about service life, but service life, and I don't know if I'll talk about it without.
Yeah, I just really wanted to sort of make that point, and how you were handling that. I mean, we saw as we were doing sort of working with portfolio a couple of years ago, I think of the 60 projects that were submitted, 25 or 30 of them were all re-roofing projects with some pretty specialized stuff down below. And it sort of seemed odd to a lot of us that people were wanting to re-roof with a 20-year membrane after the previous 20-year membrane had failed, and and they had a data center below, or they had some specialized space. And so just thinking about that and how that works.
Well, and I think, yeah, totally agree with you. And that's one that I think we tried to cover as far as talking about service life of roofs with those facilities that were called out in 1.3.9, your courthouses, those critical kind of action facilities that might be, thinking along a data center, something like that, as far as like those require a higher tier. And I believe I had that as, or I believe that's in there as a 40-year, just because like if you're doing a TPO roof that you end up having to and it's associated with risk too, and understanding kind of what do you really want to be, risking failures on something like a data center or something like that. So, and you can get the 40-year with either a thicker membrane or IRMA for sure, doing an inverted roof membrane where you're getting that protection of that membrane. So there are a couple different ways to kind of get there. Jerry.
Upstate, we went to a 40-year service life, 30-year warranties. And what we did is we beefed up the thickness of the mill thickness of the TPO. So we were using 80 mil versus everybody else wants to use 60 mil. And we did that solely because we were replacing our roofs after they were shot. They were just totally gone, and we're now begging for money, but we're leaking. And so it was decided to do something different. And continuing with that, we use extruded polystyrene, which is a little bit different. It doesn't suck water. So even if we got water into our system, we didn't lose the insulating value. And we have a system that has a torch down first. Which I know torch down people don't like that idea, but we basically made a swimming pool. Okay, and we can suck the water out. And the goodness of what we did is GAF gave us a warranty. They don't care how much water we have on the roof. They give us a warranty. No hands down. Firestone, which now has been bought out, but they gave us a warranty. And Carlisle's given us a warranty. No hassles with any of them with that. And we have longevity on one roof up in Keating. We were on year 14, not a problem. And the beauty of this is, one, we can't go any higher insulation. Our windows are in our problems. Our door thresholds, so we can't go any higher. So the only thing we're going to do later on, if in 40 years, would be just to put down another layer of TPO over the top of it and just make sure the system's dry, because you can only chase insulating value for the energy code so far. I mean, termination distance between the windows, the verticals, and the base, the flat of the roof. And you can't start tearing windows out.
Yeah. Well, and Jerry, you hit a few things. And so the DLR study, the NIB study also looked at increasing insulation. And we're actually finding that, like, the insulation that we have right now, the 30% better than ASHRAE, that payback is questionable already. Now, going to even more insulation, the paybacks are not there, which is really kind of surprising to kind of see that. So it's really tightening.
It's not to me, because I think it's the windows that's my problem. Is the insulation, the heat losses through my windows and not my roof. It's not going up the building, it's going out the building, because I always get another space between it. I got a mechanical space or something else with that. Now the problem I have with one roof currently, I don't want to things is, we tried an inverted roof system on a mechanical space underneath cooling tower, and we're having severe problems with that because that space shakes when the cooling tower shakes. And so every termination we put next to a beam, a support part is failing. Okay. And we keep getting moisture in, and it's not what we're doing. It's just that the building is a live building and it's creating havoc. So if anybody has any thoughts on how to resolve that, we've tried pitch pockets, we've tried a lot of different things, and it just fails after a while. And after a while means in like 6 months.
I'm gonna just one real quick, one thing and then Roland, I know you're next. Polyiso is the most popular roofing material. A lot of that reason may or may not be because a lot of these membrane roof manufacturers also supply polyiso, and it's kind of required to get their warranty. Polyiso goes down to an R2 at, is it 40 degrees or 20 degrees? So something to kind of, and then, thermal migration doesn't do well when it gets wet. And in the cold, I mean, there are a lot of that product, and not that that's the only one. There are, others that are not performing great either, but that product in the industry really has to kind of improve.
Well, the other thing too, Jason, with that is think of it as the same that insulation material is the same type of material that you receive when you get a floral arrangement from the florist. It's the same material. It sucks water. It hides your leak. So the industry loves it because you typically get a 1-year warranty on the guy who installed it. You get a little leak someplace, that insulation sucks the water. You lose the insulating value. And then you get the commentary from the tenant saying, well, it's not raining today. It rained 3 days ago, and now now we're getting leaks. And that's because the insulation became saturated, and now it's shedding the water afterwards, and that's the problem. And so we've gone totally away from that. We don't touch that kind of insulation anymore because of that. Polyisocyanate insulation is just it's lived its time. It's gone.
Yeah, and there's others besides XPS,
Yep.
but Roland, I'm going to jump. I know you've been waiting a bit, so let you go ahead if you want.
Sorry, I was on mute. I was just going to just real quickly say, I think the question came up about a roof system that could withstand the seismic in a Irma type configuration. And I was just going to mention, I typically will try to go with a fluid applied when I use a Irma or a PMR system. If you have the right type of deck, you can only probably do that with concrete. But in any event, for flashing, I always try to stay away from pitch pockets, and I prefer. I think the best thing is a fluid applied flashing. So you do that, you shouldn't have any problems with movement and seismic forces. And like I said, if you have a concrete deck, I would recommend that as a fluid applied membrane as opposed to a sheet membrane. Because it's definitely seamless, so you don't have to worry about seams. Even though, I know that TPO is considered seamless because it's heat welded, but a fluid applied is truly seamless. So I think that would be the best. That would be my recommendation. And in regard to the ISO, the only thing I would caution you about not using ISO is that ISO has the best R value. It has a better R value than
At 70 degrees. Yeah.
Yeah, that's true. So anyway, that's all I just wanted to mention, Jason.
Okay. Thanks, Roland. Ann,
Sure, super fast is more of a comment. Just want to thank Jason for a great presentation and lift up the connection regarding service life, because for those of you that work, to safeguard assets to the observed and expected changes of climate, that number 30 is really important. So the building enclosure, this is so vital for how we look at things and their durability and robustness to what we're living through already and what we're going to continue to live through. So thanks for Jason for bringing that up, and great presentation.
all right. Thanks, Ann. All right, got a little bit left here. Let's just try to get through to the end here. Gary, you comment roofs are often over mezzanines that have that aren't occupied with no appreciable energy savings. Yeah, that's a good point. Thanks, Ann, for your comment. Mark had a comment. I see that the building enclosure commissioning is in the general commissioning design build spec template, but not the other non-facility. I should go back and make sure that if I need to, I might have missed that. I've got the template for one, and I don't know if I have it for the other. So that's on my end. Gotta hit that. Let's see. Alexis, how was Division 1 spec and templates, AE, design build, bridging, design bid build, CX, CMA in response to the updated 2024? For example, in the testing section, the previous Division 1 was on GSA PM to ensure that the appropriate enclosure testing was conducted by an independent third party. That really hasn't changed. I think that's still, it's kind of, it's kind of on the PM to make sure that we've adhered to the P100 if we're using 2024. If I understand your question correctly, that really, the only thing is, as far as like we're clear with the E2813, the commissioning kind of enhanced commissioning for mission critical facilities and some of those facilities, and I think we actually have that in baseline now. So that shouldn't be really. Other than that, it should be no change if I understand your question correctly. All right, let me jump. Last one, chapter 3, miscellaneous, real quick. Cool roofs. This was a new section altogether with requirements for solar reflectance of the roofing. Have this information in here. The initial solar reflection at 0.85 on a 3-year solar reflectance of 0.75, and those are for climate zones 1 through 6. There's other ASHRAE 189.1. The sections are listed. So if you're looking at cool roofs, there's a new section there. And then 3.378 roof fall protection, that just got renamed. So real quick, that's everything. I think we hit some of the questions. If there are any other questions, feel free. And a couple more images.
Thanks, Jason. Great presentation. Any last questions out there before we close it out?
Yep, Nick. Okay, maybe not. Guess that's it.
All right. Thanks, everyone.
Thanks a lot.
Thank you. Thank you.